Yeah. So I'm going to talk about these new developments in the context of the kind of physics that we are working on in our group in Prague. So we study two types of collision processes. One type is the classical electron-molecule collisions, in which we are looking at elastic collisions, which means collisions in which the state of the target molecule does not change. We typically compute scattering, cross-sections, angular distributions of the electrons, and further transformation. Then we also look at the effects of nuclear dynamics, but this is something that is not implemented directly in the Armatrix codes, but we are using the data that are produced by the Armatrix codes in some follow-up calculations of our colleagues in Prague to study dissociative electron attachment and vibrational excitation. And I'm going to show you an example of a few such calculations briefly in my talk. We are also looking at electronically inelastic collisions. This is an example for pyrimidine, which I'm going to start with later on. And we are also looking at electron collisions with large molecules. This is a work that has been initiated through collaboration with Quantemol and Professor Mark Kushner, who is over there. And so we were looking at the PFAS molecules, those will be mentioned today as well, but also at the Novex molecule. Another strand of our research revolves around molecular photoionization. So this is a rather new topic, although single photon ionization is something that we have been able to do for some time, but we have made some quite big developments in the last couple of years towards multi-photon ionization, which is applicable when the intensity of the external electric field is higher but still perturbative. And this has enabled us to do some really like super interesting stuff in terms of attosecond, to study attosecond delays, ultrafast physics. And we also have the possibility to go into a fully non-perturbative regime with respect to the laser field strength. And this has been enabled by the development of fully time-dependent Armatrix theory, which was done in collaboration with our friends from Queen's University Belfast, and we have some representatives of them here. I'm not going to talk about this part in the talk, because this would be a very heavy topic on its own. But I guess it doesn't hurt at the beginning of this workshop to mention just basically what the Armatrix theory is and how it works. So the molecular Armatrix theory is a way to solve Schrödinger equation, typically in situations when one particle is very far away from the target molecule. So this would be typical setting of electron-molecule collisions. So the principle can be explained just by considering the physical picture of the collision. So if you imagine that you have an electron which is colliding with a molecule and the electron is still very far away, then it doesn't care about the details of the target molecule. So it only sees some effective potential. So this is an effectively one electron problem. So electron moving in some non-spherical potential in general. This is the so-called outer region. When the electron gets very close to the molecule, it resolves all the electrons that are in the target. So then you have to take into account for the electron-electron correlation, exchange interaction, and so forth. So the Armatrix theory solves these two regions separately and then matches the solution on the so-called Armatrix sphere, which must be large enough to contain fully the charge density of the target molecule. So in the inner region, it's basically quantum chemistry. So these are techniques of configuration interaction, but adapted to solution of a continuum problem. So you have your standard target molecule orbitals from quantum chemistry, but you also have additional orbitals which describe the electron, which is unbound. The key equation of the Armatrix theory is this matching equation, which uses this Armatrix, that's the quantity constructed in the inner region, to match the wave function in the outer region, which is this F. So the expression for the Armatrix is such that it contains these boundary amplitudes, Wik and Jk, which are constructed from the inner region solution. And the Armatrix depends on the energy for which you're solving the Schrödinger equation, and the energy dependence is analytic. So this is the really like key property of the Armatrix, because these amplitudes, you get them only once. You solve this very complicated problem only once. And then for all energies, you know how the dependence of the boundary condition looks like. So this is the key strength of the Armatrix theory. And this is why I think I would say that's maybe one of the main reasons why the Armatrix theory is so powerful for simulations of all kinds. So this is, of course, not new. It's been used for many decades. It's a multi-generational project to calculate collision data. It describes multi-electron effects on continuums. It can also be used to calculate various types of bound states, like dipole bound, reverse states, and so forth. It's a variation of a function-based method. So currently, we have the following types of solutions available in the Armatrix package. So, of course, the traditional scattering states, we can compute the photoionization states, but newly I'll be talking about what we can do with secret states and perhaps, if I have a bit of time, to talk about the multi-photon matrix elements. Then, as I mentioned, there's also the molecular Armatrix with time, which is a method that also uses the stationary solutions of the Armatrix to propagate the full wave function of the system in time, in external fields. This is extremely useful for ultra-fast physics when you have to consider explicitly the structure of time-dependent pulses, or in non-perturbative calculations when the field is really strong. So let's get into the first topic, which is the question of how to identify resonances in computed data, because formation of resonances is probably the most striking and most let's say, interesting aspect of collision processes in quantum mechanics. At least that's how it is for me. And these resonances, they enhance collision cross-sections for all kinds of processes. So this is an example of electronic excitation cross-section for pyrimidine, which is a prototype for one of the nucleobases. And it's known that electrons can damage DNA. So that's one of the motivations why we started studying this. So on the picture here, you see in the black are our calculations that were done by Armatrix calculations. And then this jagged curve is the experiment. So you can see that, well, I'm telling you that this is a fantastic agreement. Okay, the curves, yes, I know it may not seem like it for you, but it is for people who are doing electron collisions, because this is a molecule which is 42 electrons. Okay, that's a very complex target. It has very many electronic excited states. This calculation included about 30 of them. And you know, the peaks, they are all there in the experiment. That's the most exciting thing. They are shifted in energy. We know why, and it's kind of a trivial effect. That's not important. But the important thing is that all these peaks here, they correspond to resonances, or at least that's how we interpreted this in the past. But how do you actually identify the resonances? That's the question, because not every peak in a scattering cross-section is a resonance. Some of these things can be non-resonant. So typically, if you don't have any other tools, you would just have to run a lot of different calculations with different models, calculate all kinds of observables, like scattering phase shifts, time delays, and so forth. But sometimes you're still not sure. And there are also examples from other types of collision processes like photoionization, where certain peaks definitely are not resonant, even though they look like. So this is a photoionization calculation for CO2 into the various ionic states of the CO2 plus ion. And for example, the cross-section for the B state has this kind of nice peak, but that's non-resonant. It's just an onset of P-wave scattering. Whereas in the C state, there is a very pronounced shape resonance, which has a core-excited character. So you want to be able to get insight into resonances. So what is actually happening is that the scattering cross-section is computed from a quantity called the S matrix, which depends on the energy, right? And our world lives on the real axis, so we compute the cross-section for real energies. However, the resonances are actually solutions of the Schrödinger equation for complex energies. And at those energies where we have resonances in the complex plane, that's where the S matrix has a pole. So that's where it diverges. And so when we compute the cross-section on the real axis, we kind of just see, I would call it like a shadow on the wall. It's just a reflection of where the resonance is in the complex plane. So if you want to really figure out whether these things are resonances, you need the extra dimension, which is to look into the complex plane. So you want a picture like this. You want to compute the scattering cross-section, but you also want to have an insight into all the S-matrix poles that there are. So this is something that can be done with the R-matrix method because all the poles of the S-matrix correspond to solutions of the Schrödinger equation with these outgoing wave boundary conditions, and those solutions are called secret states. So in this case, this outgoing wave boundary condition includes the complex momentum K. And I'm showing you here the complex plane of momentum. In the upper part are the solutions for the bound states. That's where the wave function is exponentially decaying. Here in the lower part of the complex plane, the solution is exponentially diverging, and you have so-called virtual states and resonances which appear in pairs. And of course, calculating wave functions which are exponentially diverging is typically very hard, right, numerically. But with the R-matrix, we can do it very straightforwardly because we have the separation between the outer region and the inner region. The outer region is a simple problem, and we know what the solution is. It's this. That's the boundary condition for the secret states. What we don't know is the energy, the complex energy at which this solution appears. So that's what we have to do. We just plug in the ansatz for the outer region wave function into the matching equation, and then we just look for zeros of this function, and that gives us the energies where the secret states appear. And so that's what we do. We can nowadays scan the whole complex plane and look for zeros of this function, and we get precisely the positions of the secret states. Now, this method is not new either. It has been developed many years ago, already in the 80s by Leslie Morgan and Phil Berg for R-matrix, and then described also in detail by Quantemol in 1993. However, believe it or not, the codes have been lost. Okay, so we haven't had access to those codes for many decades. So recently we have re-implemented this whole method, but with some extensions. So before, in the past, due to computation restrictions, they were restricted to only solving for individual resonances, but now we can really scan the whole complex plane. So this gives us much more information. And by the way, of course, this is not the only way you can obtain resonances. You can also use exterior complex scaling, or you can directly compute your structure in the complex plane. But as far as I'm aware, these methods are not implemented in the general package like R-matrix is. So I'm now going to move to a part where I'm going to show you how different types of resonances behave in different molecules and how we can analyze this behavior using secret states. So the first and the simplest prototypical system is N2 molecule in collision with electrons. And in this system, we only have short-range interactions because the molecule doesn't have a dipole moment. And it leads to formation of a very famous pi-star resonance, which can be associated with the potential energy surface as a function of the NN bond length. This is the potential of the neutral state. Then I'm going to show you a molecule which behaves differently. This is HNCO. This molecule already has a dipole moment. It also has a resonance, but the resonance behaves very different. Here we have a strong dipole interaction, and there's a so-called sigma star dissociative resonance. Oh, sorry. The last example is electron collisions with Pyrrole, where it was not even clear whether such a sigma star resonance appears, and the previous calculations were inconclusive. And actually, similar picture as in Pyrrole appears in many other molecules like formic acid and uracil, and so it's a question of general relevance. So electron collisions with N2. So this is the picture from calculations of the secret states. On the top left, you see the scattering cross sections as a function of electron energy for the different bond lengths of the molecule. And on the bottom, you see the complex energy plane, and all the crosses there are the secret states. And this is the same picture, but in complex momentum plane. And so you see these peaks. There are the signature of resonances. And as you increase the bond length, the resonance becomes progressively narrower and moves down in energy, which is reflected in its position in the complex energy plane and in the momentum plane. Okay, very simple. There's nothing new to be learned. There's also some large number of these very wide states, which are describing the growth continuum. Very well known. Okay, so now we have electron collisions with HNCO. We also see a resonance at around this energy, around 3 electron volts at the equilibrium geometry. But as the bond length between the hydrogen and nitrogen is stretched, we see that although it does move down in energy, it actually does not become narrower, it becomes wider. So it dissolves in the continuum, which means that as the bond is stretched, the probability for the electron to detach increases rapidly. And then suddenly, at some bond length, a bound state appears. So this is where you can have dissociative electron attachment when the electron is attached to the NCO group and neutral hydrogen is lost. But clearly, this is a process which is non-adiabatic and requires non-adiabatic coupling between the resonance and the bound states. It's not a new phenomenon. This has been described already in the 80s, but it's often overlooked that this kind of process exists, and it's not trivial. In this case, you cannot just imagine that the electron is attached to some potential energy curve of the resonance and evolves along this straight line. This is not so easy. We need to include also the possibility for the electron to detach from the molecule and reattach again at a later time. Now the last example is electron collisions with pyrrole. So in pyrrole, there is a possibility of dissociative electron attachment, in which case, again, a neutral hydrogen is formed. And sometimes you would see pictures like this, where people would say, okay, so the electron comes in, it attaches to some kind of pi-star resonance, which by itself is non-dissociative, but then it couples to sigma star resonance, which is dissociative, and then it leads to the breakup of the molecule. Okay, but I mean, does this sigma star resonance actually exist? I mean, there's no confirmation of that. So we looked at these calculations for this molecule. We looked at calculations for this molecule, but we did this motivated by fantastic experiments of our collaborators from Prague, from Juraj Fedor, from Czech Academy of Sciences, who are able to measure two-dimensional electron energy loss spectra. So they measure electrons with various incident energies, and they measure their electron loss. So they use electrons with various incident energies, and they measure their energy loss. So in this plot, what you can then see are clear signatures of these two high-star resonances. And as you fix the energy loss, you can see how the different vibrational modes of the molecules are excited by electron impact. So in this case, they show that you have quite a strong excitement of the NH bond stretch by this pi-star resonance, apparently. Then you also have strong excitation of hydrogens which are attached to the ring. And you also have a strong excitation of the NH bending mode that's out of the plane. But the most exciting result here is the dissociative electron attachment measurement. So the red curve is showing you the measurement for non-deuterated pyrrole. The blue curve here, which has been magnified by a factor of 5, is the result for fully deuterated molecule. So this is much smaller. The black curve is the result for deuteration of the molecule at all positions except for this one, except for the dissociating one. And you can see that this is smaller by a factor of 2. And that's surprising, because you would think that if this is the bond that dissociates, the rest of the molecule shouldn't care. But that's not what they see. So they see that basically the hydrogens which are far away from the molecule, from the bond that dissociates, are strongly influencing the breakup. So this suggests that, well, we have to look for a mechanism that explains it, right? So we did calculations of resonances in the complex plane, and we found, of course, these standard pi-star resonances. We also found 2 resonances which were not previously reported. These are sigma star, but they are very high in energy. They cannot have anything to do with the mechanism in play. And so indeed, we did the calculations, and we did the calculations for different geometries, trying to figure out if any of the pi-star resonances become dissociated, but they don't. So the question is, what really happens? And we can analyze this with the R matrix, because we can look into the complex plane in 2 different configurations when the long-range dipolar moment of the molecule is switched on or when it's switched off. So when the long-range dipole is included in the calculation, we see no hole in the complex plane, no resonance that becomes bound. But when we switch off just that long-range dipole interaction, we see that there's a subthreshold resonance or a virtual state that becomes bound. So the mechanism that really is at play here is that there's no sigma star resonance as such that would be going from higher energies to lower ones, but this is an effect of a virtual state. So this is a ubiquitous effect that can be expected to play a role in highly polar molecules of all kinds. And I mean, I will not go into details of how this is calculated because I'm running out of time. I will also mention what else we can do. We can, when we have those poles, we can play with them and we can remove them from scattering data to see explicitly the effect of the resonances. So this is an example for scattering on CO2 plus molecule. So the blue line is the cross section when the resonance is included, and the dashed ones are when it's removed. So you can see these kind of things. Finally, I would like to maybe say a few words about you know, as we go to progressively larger molecules, what happens in the molecules that we have studied recently. So these are the PFAS molecules, which are like important due to the let's say environmental pollution, and they are difficult to degrade naturally because of the strong carbon-carbon bond. And there's also a molecule of Novec, which is considered as a SF6 replacement because SF6 is a potent greenhouse gas. So we did the secret state calculations for all these molecules. And what you can see is that there is a huge number of resonances in all of these molecules. And these are, of course, associated largely with these fluorine atoms, but also other groups in the molecule. And so it's clear that when we are considering any reactions that are related to these molecules, the shape resonances are going to play a big role. This is something that can be seen also from electron impact excitation cross sections. Here, full computed for this TFPS from various levels of approximation. Okay. So we can do these calculations not only with our metrics, but also with a simpler approach, which uses the Born approximation. And that's very, very useful because, as you can see from the comparison here for PFBS, at least at the lower energies, the magnitudes are fairly similar. So it's a much simpler and faster route towards some results. This data is being then used in the group of Mark Kushner to model the degradation of these PFAS molecules. Maybe Mark will tell you something about this later in this talk. And this is very exciting because what they did in their calculations is they have been able to explicitly identify the various contributions of the reaction processes to the degradation of the molecules. So you can see in some molecules the impact cross sections are actually very important contributor. It's similar to the dissociative attachment contribution. But in any case, there's still a lot of data that's missing from dissociative electron attachment, which is a challenge both for the theory and the experiment. Okay, closing time for the subject in physics. We'll not have time to go through. Okay. And maybe before I leave, of course, I have to acknowledge all the people, okay? Because this has been an effort where many people took part. So I would like to acknowledge the people from Prague, Jakub Benda, who has been a fantastic collaborator for the last couple of years. And of course, as I said, it's a multi-generational project. So the people that are listed here are only very few of the people who have actually developed the R-matrix method. The work on PFAS was largely done by Marit Sapunar and by Mark Kushner and his group. And with people from Queens, we have been working on RMT. Greg is here, who has been also working on RMT very hard. And then I would like to acknowledge people from Czech Academy of Sciences and University of Chemistry and Technology who have worked on the Carol and Novec sub-projects, and also Quantemol for supporting us in this work.
Thank you.